All right, think and rank from chapter 3, starting out with problem number 41. Jogging Jake runs along a trained flat car that moves at the velocities shown in positions A through D. From the greatest to least, rank Jake's velocities relative to a stationary observer on the ground. Call the direction to the right positive. Now, there are a few things Hewitt does not throw in here that are actually intended to be here. One, the velocities that are given for Jake are relative to the flat car, and then the velocities of the flat car are relative to the ground. Otherwise, this becomes a trivial problem. So we do have to make those assumptions, and we do also assume that the acceleration is 0 in all of these cases. So this is a sum of vectors problem, and because we're dealing with velocities and we know the vectors. So if to the right is positive, then in A, how fast is Jake going relative to the ground? Well, it's how fast he's going relative to the train, plus how fast the train is going relative to the ground. So in part A, he is traveling at -4 meters per second. The train is moving at +8 meters per second. So -4 plus +8 is 4 meters per second. Using the same logic in B, we would have 6 meters per second plus 6 meters per second plus -10 meters per second, which is -4 meters per second. C, we have 4 meters per second plus 6 meters per second, which is 10 meters per second. And in D, we have -6 plus 18, which is 12 meters per second. So they're asking us to rank Jake's velocities. So the question is, if we have D is 12 meters per second, I think we're clear that's the fastest. C is at 10 meters per second relative to the ground. That's the second one. Now the question is between A and B. They have the same speed, but they have different directions. A, he's ultimately going 4 meters per second to the right. B, he's going 4 meters per second to the left. Now, I'm not quite sure. I'm blanking on what Hewitt did in his solution, whether he said A is equal to B, in which case he's ranking speeds, or does he have A greater than B because he's going with a negative value is less than a positive value. That's somewhat misleading because going positive 4 meters per second and going -4 meters per second is just a matter of direction. There's not necessarily proper to say that one is bigger than the other. And so this is some of the confusion, and especially shows up again later on when we get to the lab for chapter 6, when we start dealing with the momentum lab, where this kind of language often confuses students. So let's just be careful out there. Be careful when you're dealing with these type problems. Problem 42. A track is made from a piece of channel iron as shown. And again, I'm assuming that you're looking at the book as you are watching these videos. A ball released at the left end of the track continues past the various points. Rank the speeds, not velocities, rank the speeds of the ball at the points A, B, C, and D from fastest to slowest. Watch for tie scores. Now, if we look at the thing about the forces acting on the ball, we have this force that is the weight, which is acting down. And then we have a normal force, which is acting at an angle, depending upon where it is on the track. So I guess it starts up here from my point of view. It then goes down. So my finger's pointing in the direction of the normal force. Now, whether this ball is rolling or sliding on a frictionless surface, we got to make one of those assumptions. If the ball is just sliding on a frictionless surface, then that's fine. If it is rolling, we do have to assume that it's a perfect roll, that there's no slipping whatsoever, and that the ball basically is going to maintain a constant energy. That is an assumption related more to chapter 7, so let's just assume it's a frictionless surface for right now. So as it slides down, the only thing that's going to accelerate it is the force due to gravity. So, because that's the part that's actually getting it to either go down, so it's speeding up as it goes down, or slows it down as it goes up. So A hasn't fallen very far, so A is going to be the slowest. B, so it gets then to the flat part, it's going to cross B. B is traveling faster than A. It drops down again, so it speeds up one more time, so C is faster than B, faster than A. And then it slows down as it goes back up the track and gets to D. Now D and B are on the same level. When we get to chapter 7, we can explain it. Perhaps we can explain it better about why the speed at B and D are the same, but they're going to be given our assumption that it's just sliding along a frictionless track. So the final rankings would be C is fastest, B and D are equal, and then A. 43. A ball is released from the left end of 3 different tracks, and the tracks are bent from equal length pieces of channel iron. I'm not quite sure why he was going for channel iron again. I'm not sure what's special. I guess the channel iron just means it's a piece of iron, so it's not soft, and the channel means that the ball is it's not going to just sliding all over the place. I'm not 100% sure what channel iron is. So, but anyway, we have this material that this ball is sliding down. Just like with 42, we're going to assume that this is a frictionless surface and the ball is just sliding without any loss of energy. So from fastest to slowest, part A, fastest to slowest, rank the speed of the balls at the right end of the track. Now, I am making the assumption that A, B, and C, when the balls are first released, they go down the slope. I'm assuming that they fall the same length. So for A, B, and C, they all slide down the same length, so they're all going the fastest speed when they get to the level spot. Then in C, they drop down one more. This is similar to part number 42. It drops down again, so it speeds up, but then it slows down again as it goes back up the ramp and back to the original speed of the level. So, but B, since I'm ranking the speeds of the balls at the right end of the track, B, it actually drops down at the very end. So if we're looking at just the speeds, A and C will have the same speed and B will be the fastest at the end. Now this is not relating to the average speed, this is only the speeds at the very end. Now part B, ranked from longest to shortest, the times, well, A gets down to a certain level, travels a certain speed. B and C both speed up. B speeds up at the very end and C speeds up in the middle. So the question is it going faster, longer for C or for B? Well, based upon the drawing, it is going faster for a longer distance in part C. And so therefore it'll have a greater average speed. Whereas in part B, it's only at the very end where it speeds up. And so in terms of time, C will be the fastest time, then B, then A. But the question is asking rank from longest time to shortest time, and so the ranking should be A, B, then C. And then for C, greatest to least, rank the tracks in terms of the average speeds of the balls. And the average speed is distance divided by time, distance traveled over the time interval. Well, the distance is the same because it says in the problem that all three tracks are the equal length. And so the distance they travel is the same. So now it's a matter of time. And so if I take distance divided by time, the bigger the time is, the smaller the fraction is, or the smaller the average speed. And so the average speed should be the reverse of the times from longest to shortest. And so the average speed, C will be the fastest average speed, then B, then A. All right, problem 44. We have three balls of different masses are thrown straight upwards with initial speeds as indicated. From fastest to slowest, rank the speeds of the balls 1 second from after being thrown. All right, so let's first talk about the language of the problem. It says they are thrown straight upwards with an initial speed as indicated. In physics problems, when they talk about the initial speed, thrown upwards with that initial speed, that is how fast it's going just after it's left the hand. That is that the speed when the hand is no longer touching it, and if we're ignoring the air resistance, which we are, then the only force acting on it is the force due to gravity. So that's 10 meters per second after it's already left the hand and it's now being pulled by by its weight. So it goes up and then comes back down. The acceleration is the acceleration due to gravity because the only force acting on it is the force of gravity. We assume that takes place on Earth, so let's assume acceleration of negative 9 meters per second squared. And the reason I say negative is when I said that the initial velocity of A is 10 meters per second, that I made that positive. It's going upwards, so up is positive. I could have just explicitly stated it at the beginning, which I did in the earlier draft of this video. The acceleration is downwards because that's the direction of the force. And so 1 second after being thrown, A is going 10 meters per second minus 9.8 meters per second, or 0.2 meters per second. Because the acceleration of negative 9.8 meters per second squared means that the velocity changes negative 9.8 meters per second each second. B starts out at 15. After 1 second, it's lost 9.8, and so it's going 5.2 meters per second. It's still positive, so it means it's still going upwards. And then C is going at 3 meters per second. We subtract 9.8 from that to figure out how fast it's going after 1 second. So 3 minus 9.8 is negative 6.8 meters per second. That means that it is going downwards. The negative velocity means a downwards direction. So But then he asks us to rank the speeds. Well, C is going the fastest. It happens to be going downwards, but it's going 6.8 meters per second. B is going the second fastest because it's going 5.2 meters per second. Because we're ranking speeds, I really don't care about the direction at this point. And then for A, it's going 0.2 meters per second. Then B, rank from greatest to least the accelerations 1 second after being thrown. Well, if the only force acting on it is the acceleration due to gravity, and the acceleration due to gravity is relatively constant as long as these three balls are in roughly the same area, then the acceleration is the same. That's why we subtracted the same number, 9.8 meters per second, every second. We did that for all of them because we were working on the assumption the acceleration was constant. 45. Here we see a top view of an airplane being blown off course by winds in 3 different directions. Use a pencil and parallelogram rule to sketch the vectors to show the resulting velocity for each case. Rank the speeds of the airplane across the ground from fastest to slowest. Now we can do this. I do recommend that you know how to add the vectors graphically. He does the parallelogram method in class. We did the head-to-tail method, which I prefer, especially if you're using more than 2 vectors, adding more than 2 vectors. But this is very similar to the pulling the stump out of the ground problem that we dealt with previously. That dealt with forces. This deals with velocities, but it's still the same math. This is vector addition. Now, a way that we can look at this conceptually is we have these 2 velocities here. We have the wind velocity, and then we have the plane velocity. And so in which of these 3 cases are the 2 velocities sort of helping each other? In which of these cases are they opposing each other? And in which cases are they perpendicular? And if you look at the diagram, B, there's an acute angle between the 2. And so when you add them together, you'll end up with the longest vector. C, they're opposing each other. And so if you add them together, you'll end up with a much shorter vector. And the hand gestures make sense in my head. I apologize if you have no idea what I'm doing with my hands there. But so B is going to be the fastest. C is going to be the slowest. Puts A in the middle, so the ranking would be B, A, C. Problem 46. Here we see top views of 3 motorboats crossing a river. All have the same speed relative to the water and all experience the same river flow. Construct resultant vectors showing the speed and direction of each boat. Rank the boats from most to least for A, the time, and B, the fastest ride. It's time to the opposite side. So let's talk about fastest ride first. That one's a little bit easier. This is very similar to problem 45 and then the stump problem from the previous chapter, that all we're doing is adding vectors, in which case is the speed of the boat relative to the river and the speed of the river relative to the ground, in which case are they sort of helping each other, which case are they hurting each other. And looking at the diagrams, C, the boat is rowing downstream as well as the river moving downstream, and therefore when you add them together, you'll get the fastest speed there, the greatest speed, I should say. And then B, they're perpendicular, and then A, he's fighting upstream. He's rowing upstream as the river's trying to take him downstream by definition. And so the 2 are sort of balancing each other out. And the way it's drawn, it looks like the boat would actually end up going straight across. So in terms of fastest ride, C is the fastest, then B, then A. Now in terms of time to reach the other side of the shore, what really is important is how much effort is being spent going across. And this has to be done based upon the drawings. Looking at them, B has the arrow that's pointing across the greatest. A is next, and then C is next. All I'm looking at is just the horizontal, from the view of the book, just the horizontal distance across that velocity vector is being drawn. So, and it's just purely about how far across, because they all have the same basic starting point over here. B goes across the longest. A stops here, so all I care about is just this part of it, and C is going down like this, but all I care about is just how much of it is in this direction. So in terms of time to reach the opposite shore, well, B will get to the opposite shore fastest, so it will have the shortest time. C will get there to the opposite side in the longest amount of time. It is going the slowest across the river. It's going the fastest overall speed relative to the ground, but it is going the slowest in terms of how fast it takes to go across. And then A is in the middle. So in terms of time, C is the longest time, then A, then B.